FlowCamp is a European training network for researchers in the field of next-generation redox-flow batteries. It consists of the work of 15 PhD students on 3 different redox-flow battery systems: organic flow batteries, zinc-air, and hydrogen-bromine. In the EU-funded project FlowCamp, a team of 5 early-stage researchers based in Germany, the Netherlands, Switzerland and Israel are working to develop a hydrogen-bromine redox-flow battery. How does the hydrogen-bromine system work?
The energy storage media in hydrogen-bromine batteries are aqueous solutions of hydrobromic acid. Since concentrations of more than 6 moles per liter can be achieved, an energy density of more than 200 watt-hours per liter is possible in theory. The reactions of the bromine and the hydrogen are both very fast and reversible. Current densities of more than 1 ampere per square centimeter can therefore be reached, which means that the system can be used with high dynamics. For example, in applications with high power pulse demands, like train grids.
What are the potential advantages?
Hydrogen and bromine are cheap and one of the most abundant energy storage materials on Earth. Since both the anion and the cation are involved in the energy storage process, the real energy density of the system is fairly high. The very fast reaction of bromine and hydrogen results in extremely high power densities. This makes this kind of battery suitable for battery systems with high power demands. For example, for frequency control in the energy grid, as well as for peak shaving.
Before you started work, how advanced was the system?
The first hydrogen-bromine fuel cell was developed in the 1960s by Boyle et al. The system was further developed at the Texas Instrument Labs during the 70s and 80s. But progress was slow due to the lack of corrosion-stable materials for hydrogen storage. With the emergence of hydrogen fuel cell cars and new hydrogen storage technologies at the turn of the century, the technology was rediscovered by Berkeley Lab in California. Currently, the startup LSTOR in the Netherlands is scaling up this technology for stationary energy storage applications.
What are the main challenges?
There are 3 main challenges for this technology. First, crossover of bromine through the membrane can lead to catalyst poisoning and therefore a reduction in power density. Second, although there are bromine complexing agents which improve battery safety, most of these agents react with conventional membranes and catalysts. And third, material compatibility, which is critical for this battery chemistry. Components such as sealing systems for this type of battery have to be sophisticated and expensive.
What progress have you already achieved?
We have constructed a mini cell stack with an integrated segmented cell. This enables us to locally resolve current densities in the cell, monitor the cell during the operation, and therefore observe the results of crossover.
We have set up a new macrohomogeneous model for the hydrogen-bromine cell, incorporating thermodynamic data of relevant polybromide equilibria and electrolyte non-ideality.
We have used electrospinning to create a low-cost polyvinylidene fluoride-based membrane with high chemical stability and less bromine crossover.
We have developed protected catalysts which are more resistant to bromine poisoning.
We have designed a new sealing concept based on surface modification by laser engraving elastomer seals. We also established a non-fluorinated and cheaper material which shows better compatibility with the whole hydrogen-bromine system.
What do you hope to achieve by the end of the project?
We would like to gain insights into local crossover mechanisms with the help of our segmented cell measurements.
We'd like to validate our macrohomogeneous models and to be able to predict how the cell will react under different conditions.
We'd like to prove that our protected catalyst can significantly increase the lifetime of hydrogen-bromine cells.
With the method, it is possible to produce tailor-made seals with well-known technology which enhances safety and reliability.
The hydrogen-bromine redox-flow battery is one of 3 next-generation batteries that are being developed in the FlowCamp project. For more information, please visit our website at www.flowcamp-project.eu.